Everyone, welcome back to my channel. I'll show you the 1983 Pontiac. It's a catalog from 1983. Exciting new 1983 Pontiacs you are going to see and read about on the following pages were not created overnight. On the contrary, they are the result of thousands of hours of thinking, planning, and hard work by thousands of people who are dedicated to one goal: to be known for cars built with innovative styling and engineering that offer excellent performance and roadability. To reach this goal, designers and engineers have worked closely together on a continuing basis to help ensure that each Pontiac model has maintained its character with the proper combination of acceleration, handling, comfort, and efficiency. It's a concept we call total performance, and it is basic to the Pontiac philosophy of driving excitement. On the next few pages, you will find an exciting explanation of the kind of work that goes into the development of every new Pontiac. How an idea becomes reality. What makes a car a Pontiac? So, sit back and enjoy the ride. You're about to take a trip to excitement. Important. A word about this catalog. We have tried to make this catalog as comprehensive and factual as possible. Since the time of printing, however, some of the information may have been updated. Some of the equipment shown or described is available at extra cost. Before ordering, you should be brought up to date. Pontiac Motor Division reserves the right to make any changes at any time without notice in prices, colors, materials, equipment, specifications, and models. Check with your Pontiac dealer for complete information. Fortunately, Pontiac went out of business, so definitely could not check with a Pontiac dealer because they do not exist anymore. Pontiac body engineering and aerodynamic design. With Pontiac, a car begins as a concept, a dream to build an exciting automobile. This dream may be born in the mind of an engineer, a designer, or in the collective consciousness of many automotive wizards. Wherever its birthplace, it is a job of design staff to grab hold of the dream and help it take shape. In its incubation stage, the dream starts out as a series of fine line sketches, explorations of various configurations in which the total package could conceivably exist. When a sketch appears that captures the essence of the car's objective, the next step is to tape it up full scale. The trick here is to retain its character and engineering attitude while dramatically increasing its scale. At this point, a two-dimensional dummy is introduced to incorporate human concerns, including seating, comfort, visibility, and control accessibility. And they actually forgot to put a comma right here. After visibility, it's supposed to be a comma. Once the designers have some of the proportions and contours roughed out, they can develop a small-scale model. Then the full-size clay model is shaped by conventional methods on a rigid steel armature to which, if necessary, designers can attach wheels and chassis components. When the design is final, the model is then scanned. An operator uses a digitalized light beam measuring device to rapidly and accurately record thousands of points along the model's surface. This final record becomes the raw data input for an advanced computerized acquisition and control system called Cadence. Complex mathematical formulas within Cadence enable designers to smooth out and refine the raw data. This procedure replaces endless hours spent at drawing boards. The mathematical model can now readily be assessed by design or engineering departments to determine if the design meets specific allowances, such as structural rigidity, wheel clearances, and engine compartment requirements. This defined data from the computer can then be programmed directly into the milling machine, which recuts the new master model out of clay or wood for final surface rechecking and wind tunnel testing. Many people think of aerodynamics strictly in terms of fuel efficiency, but that tells only half the story. Certainly, a low drag coefficient is necessary to help achieve fuel efficiency, but to determine a car's true aero efficiency, you must multiply its drag coefficient by the frontal area, a square, or CD times a square equals aero efficiency. A bus, for example, has one of the lowest CDs on the road, but its frontal area is so massive that its total aero efficiency rating is worse than even the boxiest of cars. At Pontiac, aerodynamics goes miles beyond fuel economy. Through our work at the GM wind tunnel, we've discovered that by redirecting the flow of air, we can reduce wind noise, improve ventilation, maintain surface cleanliness, enhance engine cooling and carburation, and more importantly, fine-tune vehicle ride and handling. You see, after designers receive the aerodynamic data in the wind tunnel, they feed this information into a computer. The computer pinpoints high and low pressure zones along the vehicle surface. These zones determine how the vehicle will perform in typical driving situations at high speeds, in crosswinds, or while passing trucks. Trans Am hood scoop, for instance, faces the windshield to exploit a high pressure zone shown in red diagram below and channels cool air into the induction system for improved performance. The science of aerodynamics is one of the many tools used in the design of a Pontiac Total Performance. Our 1983 Trans Am is a clear indication that it will always be an important factor with us. The hood scoop directs air into the induction system from a high pressure zone at base of windshield. Flow through side windows help eliminate turbulence, reduce wind noise, and help keep the glass clean. Front and rear flush glass adds aero consistency to the body shape. Rear aero wing spoiler raises the trailing edge of the body to smooth out air turbulence, leaving the car. Concealed headlamps contribute to the overall flush body shape. Front air dam directs air around the body, keeping lift forces to a minimum. Front and rear wheel skirts channel air away from the wheel housings to keep it flush within the body. Flush wheel covers help smooth out the airflow over wheels and tires. Some nice bowling rooms there, must say. Driver environment design. To many drivers, a car is like a home away from home. To a lot of us at Pontiac, it's the same way. When we head out at the parking lot and take off down Wide Track Drive, we don't always take the shortest way home. And because we spend so much time in our cars, a lot of long days and late nights are spent designing the driver environment of your Pontiac to make it as comfortable as possible. But this is not the kind of comfort you find in your living room. It's the comfort knowing that you're in total control of your driving environment. A big part of this control comes from being in touch with your car. In the past, it was popular to isolate the driver from the road and engine noise, but through human factors research in the development of the Pontiac 6000 ST, we discovered that some sound frequencies can enhance driver awareness. So Pontiac engineers adjusted the acoustical insulation to alter the character of the sound. Lower frequencies are allowed to enter from the engine, and higher frequencies from the tires. These frequencies, though barely audible, open lines of communication between you, the powertrain, and the road. Another example of how Pontiac engineers put you in a closer touch with your car is through a device known as a Driver Information Center. You'll find it in the instrument panel of every Pontiac 6000 STE. The Driver Information Center is a liquid crystal graphic display that tells you the temperature is high and when fuel, oil, coolant, and washer fluid is low, when the hood or trunk is open, and which door is ajar. The Driver Information Center also allows you to check your headlights, high beams, turn signals, brakes, and tail lights, all from the driver's seat. It even reminds you when it's time to change your oil and filter, rotate the tires, and tune up the engine. One of the more vital aspects of the driver environment and one of the most overlooked is your car's heating and ventilation system. Stale air and temperatures that are too warm or cold can cause fatigue and distraction while driving. So, Pontiac engineers pay particular attention to the design of climate controls. The STE's heating, ventilation, and air conditioning system, HVAC, for instance, uses advanced electrical controls with light emitting diode locators so you can accurately adjust the temperature of the air for a climate suited to you. The entire time you are in your driving environment, you're sitting down. While you're there, the people who design Pontiac seats want to make you comfortable. Again, it's not the kind of comfort you find on your sofa. Bioengineers work closely with orthopedic consultants to design seats that offer you firm, secure support. Seats that conform to your spine, individual driving position to help optimum visibility and accessibility to driver controls. In fact, They're seats that fully adjust to conform to the driving positions of more than 90% of the drivers in America. Standard driver's seat in the Pontiac 6000 STE has 6 separate body adjustments, including seat height and angle, backrest angle, and headrest height and angle. The seat also features thigh support to help reduce leg fatigue and lumbar support to reduce back tension that can cause drowsiness. Notice the concave shape of his seat. It's designed to help keep you comfortable as you round tight comes. This is what we mean by the comfort of total control. If you're accustomed to more cushy, passive cars, we invite you to experience this feeling. We think you'll find it refreshing. The articulating bucket seat, available on 1983 Firebird and Pontiac 2000s, are biomechanically engineered to fit your body like a pair of designer jeans. The articulating seat conforms to your individual driving position through 6 different areas of adjustment. A. Seat angle. B. Adjustable headrest. C. Back and seat lateral support. D. Thigh support. The articulating bucket seats also feature fully adjustable lumbar support, not demonstrated here. Pontiac. Fit and finish. At Pontiac, we know that the best concept or design is useless without equally high standards of production quality. So, to assure quality that will serve the total performance of your new Pontiac for thousands of miles, we employ some of the latest production technology. Take a walk along the assembly line in Norwood, Ohio facility where some of our Firebirds are built, and you will see this new technology in action. Electronic robots perform more than 2,000 intricate welds on each body. Computers analyze entire electrical systems and can pinpoint defects in even the smallest wire. Laser scan front ends, door frames, and tail assemblies to an accuracy of 3 millimeters. All this input is fed into the master computer to determine which areas are consistently turning out quality fit and construction, and to identify and rectify any recurring problems. Before the first drop of paint is sprayed onto a Firebird body, the metal is sanded, rubbed, degreased, and cleaned thoroughly. This fine finishing is necessary not only to give the paint its high gloss luster, but more importantly, to provide stronger adherence of the primer coats for the metal for rust protection. The primer coats are applied to metal in a special bath called cathodic Alpo dip. This is an electrophoretic paint process in which the body is given a negative charge and the primer paint is given a positive charge. When the car comes in contact with the paint, 2 poles are magnetically attracted to each other, and the primer is drawn into the cavities and crevices we could never reach through spraying and other dipping methods. Sealers are applied to the interior metal. The wax is injected into the body cavities to provide further anti-corrosion protection and to mute road noise. Newly developed stone chip protection is sprayed along the underside of the exterior. This smooth urethane-based coat helps protect the exposed paint surfaces against road salt and rocks. Once the protective primer coats are applied, the body is ready to be painted. Every Firebird is then cleaned, painted with a top coat, and baked. This process is repeated at least 2 more times, not just to make your new Firebird look good, but to provide a thick shield that will keep your Firebird looking good even when it's not so new. All metal parts of the car are painted together. Before they go into their different areas of assembly. The master computer tracks the parts and reunites them for their final assembly. This way, the color of the hood, doors, and body match precisely. Until recently, paint was sprayed on manually using high solvent, low solid paint. It was necessary to dilute this type of paint in order to maintain a fine, even spray and avoid streaks or runs. Today, by the use of robotics, we have achieved a consistently precise spray pattern. We also use what is now known as a turbo bell disc. This procedure employs centrifugal force to separate the paint. The disc spins at ultra-high speeds, driving the paint off the disc edge into a fine mist, which is then magnetically attracted to the car body. Again, the paint and body are given opposite electrical charges to assure the entire surface is covered. This process enables us to use high solid, low solvent enamel paints for thicker, stronger, high gloss surface that helps resist chips and scratches. Finally, before a model leaves assembly line, the body is hand buffed and polished. These new procedures and technologies exist not to speed up the mass production of vehicles, but to assure consistent quality so that every Firebird that rolls off the assembly line looks as great as the one before and performs as well as the one following. These advanced production techniques will help keep your Firebird performing for years down the road. So you've got your wax, sealer, Opal primer, steel, zinc-rich primer, stone chip protection, and top coat paint. Power and drivetrains. In recent years, more and more America's drivers found themselves facing a difficult question when selecting a new car, one with power or one with efficiency. It seemed you can only get one or the other, and it quickly became a problem. Fortunately, this was the kind of problem that innovative engineers thrive on, and one that they've worked very hard to solve. The beauty of Pontiac's concept of total performance is that every Pontiac model is designed and engineered to provide An exciting blend of power and efficiency that's not only right for today, but also consistent with each model's character. To achieve these proper combinations, engineers are constantly testing and experimenting with the engines and transmissions of today. With the knowledge they obtain from this work and the use of advanced technology, they are seeking new ways to improve the design, quality, performance, efficiency, and durability of the powertrains of tomorrow. On the next few pages, you will see how the engineers' hard work has paid off in the powertrains available in the 1983 Pontiacs. Overhead cam performance. To achieve total performance, it is crucial to develop the kind of power plants that are necessary to make this concept a reality. Engines today must be lightweight yet durable, technologically advanced yet efficient. The 1.8-liter overhead cam four-cylinder engine in our 83 Pontiac 2000 is a prime example. For strength and durability, this new OHC engine features a deep skirted cast iron cylinder block, nodular iron crankshaft with five main bearings, nodular iron flywheel, hardened valve seat inserts, chrome plated intake and exhaust valve stems, bifold exhaust valves with stellite faces, exhaust valve rotation caps, nodular iron exhaust manifold, and weight selected iron connecting rods, which also aid in reducing vibration. This deep skirted cast iron block also helps in reducing noise and vibration. So does a balanced crankshaft with the 8 counterweights, the 5 main bearings, balanced flywheel, and the CCIA/C system, which stands for Controlled Compressor at Idle, and which helps eliminate engine cut in and shake. Also aiding in quiet operation are the pistons, which are close fitted to a bore clearance of 0 to 0.020 millimeters. To help make the OHC engine lighter, the cylinder head, camshaft support, cam cover, oil pump housing, intake manifold, and pistons are all made out of aluminum. Smooth, responsive performance is another important characteristic of OHC engine, and there are several key features that work together in this achievement. The low back pressure exhaust system, quick opening throttle, high torque transmission converter, and good low and torque of the OHC engine combined with its electronic fuel injection system to provide the responsive drivability that is so important today. To achieve this responsiveness, fuel delivery, engine spark, advance, idle speed, and the torque converter clutch are all carefully controlled by the EFI system. A horizontally mounted electronic spark timing EST distributor directly driven by the camshaft allows for precise spark control in combination with the OHC's other performance. features. Result is impressive drivability and fuel economy. Quality is another outstanding characteristic of the new 1.8-liter overhead cam four-cylinder engine. It's reached through the development of our modern engine manufacturing plants, which allow for critical inspections throughout the manufacturing process. For example, every OHC engine receives two loaded hot tests before final approval. During assembly, key components are automatically inspected on the line. The crankshaft itself receives 79 dimensional checks. The camshaft 26 dimensional checks. Other procedures to help achieve quality include the diamond honing of the crankshaft and cylinder bores, and the automatic torque monitoring of critical fasteners. Serviceability, like quality, was once another important consideration in the design of OHC engine. Predetermined placement of such key features as the cam-driven distributor, spark plugs, thermostat, and fuel filter help to provide easy access and service, and it all helps make the OHC engine even more enjoyable. Computer monitored engine controls. One other important aspect of the electronic fuel injection systems in both the OHC engine and the 2.5-liter four-cylinder engine is the actual brain behind it. It's an electronic control module, a tiny onboard computer on every gasoline-powered Pontiac ECM is designed to receive inputs from various sensing elements throughout your car. Upon receiving this information, which is updated many, many times per second, the electronic control module monitors engine actuators such as the fuel injector, idle air control, motor, EST distributor, and torque converter clutch in a pre-programmed manner to help aid drivability. ECM is also largely responsible for monitoring the precise regulation of the engine's air fuel mixture in all types of driving conditions and at all altitudes. It allows for optimum conversion efficiency in the catalytic converter and enhances the 1.8-liter (2.5-liter) engines to meet all federal and California exhaust emission standards. More impressive performance. 2.5-liter four-cylinder engine, available in several of our 83 models, is another exciting marvel at the advanced technology. Like the OHC engine, the 2.5-liter four-cylinder engine is designed for smooth, responsive operation. Standard electronic fuel injection is utilized to precisely control such engine functions as fuel delivery, idle speed, and engine spark advance. The result is improved drivability and fuel efficiency One of the basic elements in producing responsive performances in the four-cylinder engines is the development of high torque at lower engine speeds. Determined engineers who have worked very hard all over the years to achieve this goal, and their persuasiveness has paid off. The 1.8-liter OHC and 2.5-liter four-cylinder engines have been designed to help provide its maximum torque even at low speeds. The torque charts at upper left and below clearly to indicate the high points of both the torque and engine speed of these four-cylinder engines. The result, as planned, is consistent, responsive drivability. Engineers are always confident that a better engine or lighter, more durable engine part is just another test or experiment away. To reach their goals takes a lot of hard work, long hours, and personal dedication. It's really a matter of pride, and just another reason we're so proud of the 1983 Pontiacs. And here's the 1983 2.5-liter engine performance diagram. Getting the power to the road. Whether a car should have front-wheel drive or rear-wheel drive is a question engineers spend a great deal of time analyzing. It's not an easy decision because each system has its own advantages. For example, front-wheel drive provides a trimmer car with more interior space, while a car with rear-wheel drive may offer better overall balance. The main thing is that the engineers always make this decision with the character of each model in mind. Another feature that can add to a car's character and to your driving enjoyment is its transmission. Simply put, a difficult transmission can make you dislike an otherwise nifty car, while a smooth transmission can easily make a car a lot more fun than you ever thought. The new standard 5-speed manual transmission in our 83 Firebird SE and Trans Am is an absolute delight. It's smooth and easy. Well, I gotta agree with this one with them. Definitely is an absolute delight. I've got 5-speed right here. And it's the biggest delight in the world. Anyway, let's go back to the story. With gear ratios that have been specially matched to the performance of both the high output V6 and 5.0 liter V8 engines. The beauty is that the fifth gear overdrive helps improve highway fuel efficiency and acceleration while reducing engine noise and wear. The 4-speed automatic available in our 83 Firebirds is another overdrive transmission you're going to appreciate. Ease of driving, smooth operation, and increased efficiency are all a result of its torque converter clutch, which helps to combine the best features of automatic with those of a manual. Our Pontiac 2000 also has a new transmission for 1983. It's a standard 5-speed manual with the electronics fuel-injected OHC engine. Designed with a performance level 3.83 final drive ratio. It's both easy to use and fun to drive. And there's a 5-speed manual Pontiac 2000 right here. Engines described here are just a few of the many power plants available for the 1983 Pontiac lineup. They're the kinds of engines we feel are necessary to achieve our goal of total performance. 1.8 liter overhead cam, OHC 4-cylinder engine with electronic fuel injection, 2.5 liter 4-cylinder engine with electronic fuel injection, 2.8 liter high output V6 engine, 5.0 V8 engine with crossfire injection, specifications: horsepower 84 at 1500 RPM, torque 102 ft pounds at 2800 RPM, compression ratio 9.0, borax stroke 3.34 times 3.13, cylinder block and head cast iron, intake manifold aluminum, crankshaft nodular cast iron, exhaust manifold nodular cast, exhaust system single with Cadillac converter. Ordering code LH8, and this is model Pontiac 2000, 5-speed manual transmission, the 3.3 axle ratio. And we'll go back to 2.5 again. 2.5's got a horsepower of 9,400 at 4,000, torque 134 ft pounds at 2800 RPM, compression ratio 8.2 semicolon 1, ball X stroke 4.00 times 3.00, cylinder block and head cast iron, intake manifold aluminum, crankshaft nodular cast iron, exhaust manifold stainless steel, exhaust system single with Cadillac converter. Ordering code LQ9, LR8, LR8, and LQ9. It's too bad they went out of business. And that's for Firebird Phoenix LJ, Pontiac 6000, and the Firebird SE. And its characteristics are 4-speed manual, automatic, and 5-speed manual, with the axle ratio of 3.42, 3.32, 2.39, and 3.73. Next, we're going to go back to the 2.8 liter high output V6 engine. Horsepower 135 at 5400 RPM, torque 145 ft pounds at 2400 RPM. Compression ratio 8.9 semicolon 1. Ball X stroke 3.50 x 2.99. Cylinder block and head. Cast iron. Intake manifold aluminum. Crankshaft modular cast iron. Exhaust manifold cast iron. Exhaust system single with Cadillac converter. Ordering code LH7, LH7, and LL1. This included the Pontiac 6000 STE, Phoenix SJ, and Firebird S-E. And they were automatic, 4-speed or 5-speed, with the axle ratio of a 3.33, 3.32, and 3, and a 2.39, and 3.73. Then we've got the 5.0 horsepower, 145 at 4,000 RPM. Torque, 240 FT-LBS at 1,600 RPM. Compression ratio 8.6 semicolon 1. Ball X stroke 3.74 x 3.48. Cylinder block and head. Cast iron. Intake manifold aluminum crankshaft. Nodular cast iron. Exhaust manifold cast iron. Exhaust system single with Cadillac converter. And the ordering code for this was LG4. Trans Am. Automatic. With an axle ratio of 2.93. I'll let you guys look at the engines again. Fortunately, that they stopped producing Pontiac vehicles. Maybe they'll come back in business one day. Who knows? Suspension design and development. One of the most important roles in creating a new Pontiac is played by the suspension design and vehicle development engineers. When you think about it, the single most important factor in determining a car's character is the feel you experience when you grip the steering wheel and set down the road. How a car reacts in a lane changes situations over rough roads, and in a freeway, driving has a profound effect on how you perceive it, and often whether or not you will become an owner. Excelling at developing the special road feel has been a Pontiac tradition for the past 25 years, which is why Pontiac has been responsible for some of the most exciting driver's cars America has ever produced. Suspension design and vehicle development is as much of an art as a science, as much human touch and evaluation as its computer models and laboratory tests. The design tools of suspension engineer are computer programs that model the actual suspension geometry, which determines the requirements of the suspension components. Finite element stress analysis is used to project input loads of a suspension model on a computer screen to analyze the stress capability of a system. The analytical tools of a suspension designer include laboratory fatigue tests on prototypes, which will indicate their ultimate strength and durability. The finished suspension design is then measured on prototypes of the GM proving grounds to see that it meets all durability requirements under normal use, as well as abusive use. Componentry is then altered, redesigned, or refined from this data. When suspension development engineers take over, they perform the critical task of evaluating the suspension package within the constraints of the vehicle design. They are responsible for tuning the vehicle suspension components to see that all goals are met. As you can see, suspension design and vehicle development is much more than just springs and shocks. From Pontiac 1000 to Bonneville, the vehicle must satisfy its own ride and handling requirements. But above all, it must ride and drive like a Pontiac, which is really what it's all about. Front wheel drive, the concept. When Pontiac suspension development engineers set out to tune the components for the new Pontiac 6000 STE, they accepted a tremendous challenge. The STE would be one of America's first front-wheel drive luxury performance sedans and most technically advanced Pontiac ever built. The first crucial decision centered around the Pontiac 6000 STE's wheel and tire combination. After several high-performance radials were evaluated, Goodyear Eagle GTs were selected to complement these thoroughbred tires. The first pore-free die-cast aluminum wheels ever offered on a production car in the U.S. were developed specifically for the STE. Their lightweight and extreme strength underline their functional beauty. The shock absorber, valving, and spring rates of the Pontiac 6000 STE are tuned for stability without sacrificing comfort. The front stabilizer diameter increased, and the addition of a rear stabilizer keeps the cornering altitude as level as possible. The power rack and pinion steering gear ratio is improved for fast steering response and added sensitivity to driver input, and the ventilated power front disc brakes are helped by finned aluminum rear drums for consistent performance. The most dramatic suspension feature of the Pontiac 6000 STE is its sophisticated electronic ride control system, ERC. This system automatically maintains the proper ride altitude from up to 5 passengers, plus cargo loadings. The objective of ERC is to maintain consistency in comfort and ride as loadings are increased. Pontiac suspension engineers have achieved their goal in the Pontiac 6000 ST, combining STE, combining the contradictory elements of ride and comfort and exhilarating driver-oriented performance. The STE reaches a plateau in ride sophistication formerly reserved for some of the world's costliest sedans. Thanks so much for joining me, guys. I'm going to take a break with this catalog. I've got many pages already read. It's all about 1983 Pontiacs. So I'm going to take a quick break, and I will be back tonight to finish the rest of this catalog. I thank each one of you for joining in on my channel and learning some about 1983 Pontiacs. I appreciate all of you and hope to see you all again soon.